Hello everyone, I hope you are doing well. So today we're going to basically continue off the multiple choice section of the 2024 VCE chemistry paper that was basically that students done today. Please use them, to check your answers. Again, these are suggested solutions. Please, if you see any mistakes or something, just let me know. I'll have a look at them. And yeah, I heard that a lot of people said, of course, the multiple choice section is hard. And so yeah, let's just continue off from it. So, question 16. A reaction between iron ions and thiocyanate ions produces iron thiocyanate ions, and this is the reaction. So we can see that it's an exothermic reaction. All right, a few drops of sodium thiocyanate solution are added to 200 milliliters of equilibrium mixture at a constant temperature. The concentration tile graph shows the change in concentration of the SCN. So the thiocyanate. Okay. And of course, because they added thiocyanate, this increases, of course, in the concentration. And you can see that spike is over here. Which of the following statement is true? The equilibrium constant at T4 is lower than T1. So we're saying the equilibrium constant here, T4 here. So the equilibrium constant at T4 is lower at... the equilibrium constant at T4 here is lower than at T1. Absolutely wrong. Remember, equilibrium constant only changes for one variable, and that's temperature. The equilibrium doing anything like increasing pressure or, doing other stuff, adding reactants or changing volume, all these don't have an effect on the equilibrium constant. Only one variable, and that's temperature. Because we are making sure that it's, we're not playing around, there is a constant temperature. The K value is actually constant. It doesn't change. So this is absolutely wrong. Next question part there. The chemical energy of the system increases between T3 and T4. So T3 is here. And T4. So T4 is when it reaches, again, reestablishes equilibrium. Let's have a look. Well, so let's think about it. If you're increasing SCN, like using, the Chatelain's principle, the system's like, wait, that's too much SCN. I need to find a way to, get rid of it. And so it's going to move forwards. And if it moves forwards, you got to think of it. Okay, if it moves forwards, because it's an exothermic reaction, the forward reaction is exothermic, it's going to release energy, that chemical energy. Hence, the actual chemical energy is going to be decreasing. For this process over here, it's going to be decreasing that chemical energy. The chemical energy of the system increases. Nope. So you remember we said decreases. See, the rate of the reverse reaction is less than the rate of the forward reaction at T3. What I'm going to do is I'm going to just try to sketch a nice diagram to represent the rate graphs to kind of explain this. All right, that's time. That's your rate of a reaction. So, okay, let's think. So, let's make the blue color forward, and the red color here, backwards reaction. So, the backwards reaction. Okay, so when we're looking at the forwards reaction, what's happening? Well, they've increased you can see they've increased the, basically what they've done is they've increased, SENS, and what's happened is that the forward reaction has happened. So it's increased the forward reaction. So imagine at the beginning here, they are both at equilibrium, so put them on top of each other like this. But then what's going to happen is the forward reaction spikes up because as we can see here, you're increasing SENS and it moves to the right. So the forward reaction, because there's a lot of reactants, remember? Think of it. You're increasing SCN, so the molecules, you're increasing the concentration. If you're increasing the concentration, there's a lot of collisions that are happening with these. And so that, increases the rate of the forward. And so, of course, over time, after that, while the concentration of this is starting to increase, this also... there's enough products that this goes also, the reverse reaction also happens too. So as the reverse happens, the forward reaction will become like this. It'll become actually smaller. Whereas the reverse reaction, it's going to start also coming up. And so they're going to reach equilibrium again here. So somewhere around here, let's say. Again, this is just like a example one. It's not an actual, right one, but it just gives you kind of a really easy look on what's happening in terms of forward and backwards rates. Remember, when we're talking about rates, we're talking about like all collision theory here. So let's think about it. Okay, so what we said was, okay, so T1's here, by the way. It's at equilibrium, and this is here at T4. Because that's where equilibrium occurs, reestablishes. T3 is T2 is the change, so it's here. So T3 must be in between here. So we're looking at T3. It says the rate of the reverse reaction is less than that. So let's actually look at these. I'm going to use this color here to really look. So at T3, what's that? Yep, at T3. So at T3, this is the rate of it. So around here. And this is the rate of it at here. So we can see that the rate of the forwards is actually larger than the rate of the backwards. The rate of the reverse reaction, yes, so the reverse, the red one, is less than the rate of the forward at T3. Yes, it actually is. That makes sense. So I'd say C is the answer there. And you can kind of explain it there. Both the concentration of, let's have a look at the last one. Both the concentration of Fe and SNE are higher at T3 than T1. I mean, we can really easily check that by just kind of making up some values. Like, not making up values, but kind of, let's say, imagine this is here. Say this here is the, let's actually draw it nicely. Like, let's say this here is the concentration of SCN. Oh, no, I've already got that there. Fe3 plus. Now, let's think about it. What's happening is because you've increased this, they moved, of course, it shifts to the right. This is going to start decreasing. It's going to nicely start decreasing. This one over here, let's say we draw this one over here, which is the concentration of this, by the way. FeSCN 2 plus. This one over here, because it the forward reaction is happening, so it's going to move like this. Okay, it's going to look like this. So what the question says is both the concentration of Fe and Se are higher at T equals 3 than T1. That's false because you can see that Fe3 here, it's actually higher at T1 than at T3. But yeah, it works for this one, but not Fe3 plus. So that's absolutely rubbish. So that makes sense. So your only answer would be C for question 16. I hope that makes sense. Perfect. Question 17. Let's have a look at this part here. A piece of blister copper containing 98.5% copper. The blister copper also contains other metals, including silver, iron, and nickel. Electrolysis in an aqueous solution of Cu2 plus ions is used to produce 99% pure copper from a blister copper. In the electrolysis of the blister copper, you know what this reminds me of? There's actually a similar question like this on the 2023 VCA, last year's exam. In that last question, there's a question like this, and yeah, it looks like the same question. In the electrolysis of the blister copper is used as a cathode. Okay, let's think about this. Let's break this down. I'm going to draw, let's say, an electrolysis here. Electrolytic. Okay. So, let's draw these. This here is the. Think of it like, yeah. So these here. Okay. I'm going to call this the cathode here. Normally the cathode, remember the cathode is the one, and this is the cathode, sorry, and this is the anode. Now, think of it like electroplating. Just think of it like in terms of electroplating. We know that cathode is the one that gets electroplated. So imagine that this is like, actually, let me draw, like, let's draw that circle. Like, imagine this is a circle. And this is the copper that, so this is the copper, let's call this the copper, this has to be the copper, the blister copper. Blister copper. Because that's where taking the resources from to, not electroplate in this question, but to form pure copper. So this becomes pure copper here, by the way. That's pure copper. Yep, so again, you'll bring it there. So that has to be the cathode, and that's the anode. Yeah, the blister copper is used at the cathode. Nope, it should be used at the anode. That's wrong. A solid ion falls to the bottom of the electrolysis cell. Well, to check that, what we're going to need to do is we're going to look at actually in our electrochemical series and highlight what's happening here. So what do we had? We had copper solid, of course. Where's copper solid? So we have copper solid and also ions. We also had water, so don't forget water. We also had what else? Of course, silver, silver, which is Ag, nickel, iron, all solid. Yeah, so all of these here. Now let's think. What's really going to happen here in this cell is that, of course, the strongest reducing one, the one that's going to get reduced, is this copper 2 plus ions to copper solid. And the strongest oxidized one, which is, is this one. The iron will turn into iron, ions, like iron ions. So the question says solid iron falls to the bottom of the electrolysis cell. No, it doesn't fall at the bottom, and it's not solid. It's actually what's going to happen is it's going to become, we're going to form in the in the electrolyte Fe2 plus ions. It doesn't actually fall to the bottom. It just becomes Fe2 ions, and it's an electrolyte. And also, the one that actually falls, if you don't know, is this. So imagine the reaction. Okay, so because we have little iron, of course, and of course, these are just, we only have little parts of this. It's not mostly copper, of course. So what happens is, when this iron runs out, when it gets all turned into Fe2 plus ions, what's going to happen is this. This runs out, and then this one also becomes, the nickel 2 ions will also release too. And then after that one runs out, and then we actually get into copper, like this actual copper solid. So we're going to have these two reactions actually just opposing each other. This one's, getting oxidized, this one's getting reduced. And yeah, until when the reaction stops, this, silver, it's going to be left out. It's going to be so silver is the one that's going to be left out. Basically at the bottom, or like, it's called anode mud. So left out at the end. So that's actually silver if they talked about. That would have been right. See? The 99% pure copper product should be removed as it forms absolutely rubbish. Now, that's not normal. You wouldn't remove... Think of it. You wouldn't actually remove copper. Like, look, if it's forming... Look, let's say the reaction has been completed. Yes, you can remove it. But then if it's still being formed, that really affects all of the chemical equations here. There's going to that doesn't make sense. I've never seen a question where you would take off while it forms. That's absolutely wrong. You can't. I've never seen a question from that. Because it just affects everything, the electrochemical equations and stuff. So, D, the concentration of copper 2 ions in the electrode changes during electrolysis. Now, it does actually, because if you think about it, these, you might wonder, you're like, hey, but aren't these just going to be like copper 2, these just, let me just go back. Okay. So aren't these here, these two, after, these have become, have turned to ions in the electrolyte, aren't these just going to, be this oxidizes and this reverses, and aren't these just going to, like, for example, this uses this, so when it's getting reduced to Cu2 plus ions, isn't that going to decrease the concentration of Cu2 plus ions? But also, when the copper is getting oxidized, isn't it just going to reform them? So this is constant. You believe that this is constant formation, but that's wrong, because remember, don't forget, we also had this iron, this nickel that also became, like, at the start, that was turned into iron. So it's actually not going to be like a constant temp. Like, it's going to change over time, because we had these two at the start. Yeah. So the concentration of ions and electrode changes during the electrolysis, absolutely, because we form these two first, and then we form these. So there will be likely more copper 2 plus ions at the beginning. So these sounds right. These are the best in that one. Really kind of getting into those hard questions over here. Damn. All right. Okay, that looks all right. 17D. Next question. Each of the following compounds has a molar mass of 88 grams per mole. Which of the following has the highest boiling point? Really nice question, because why do they give us actually, if they all have the same molar mass, it means that they all have around the same dispersion forces. So we don't have to use dispersion force. So which of the following has the highest boiling point? Now, to find the boiling points or physical states like melting points or anything like that, we need to look at the intermolecular forces. So let's look at the first one. What are the intermolecular forces? Excluding dispersion forces, because they'll all have the same around dispersion forces. So for the first one, it's C O C, and then C here. So it's actually an ester. So an ester here actually only forms dipole to dipole bonds. So this one over here is only dipole to dipole. So dipole to dipole. Okay, this one over here, so this one over here is, it looks like, yeah, it's a carboxylic acid. So straight away you can see at the end it would be a carboxylic acid. Now, carboxylic acid, it has an OH here. This actually forms hydrogen bonding. It's the strongest hydrogen bonds, but also this COO actually forms dipole to dipole too. So this one actually has both of them. So it has hydrogen / dipole to dipole. So this one actually has, yeah, good. This one, okay. Next one. All right. Next one, this one over here, it only has OH, which is, of course, hydrogen bonding. It's an alcohol. Hydrogen bonding. This one over here also only has hydrogen bondings. It's N to H. So these N to H only form, remember, hydrogen bonding is only formed from oxygen reactant like OH or NH or FH. I've never seen FH, but yeah, when it's oxygen, and when oxygen's close to hydrogens, nitrogen, fluorine, all these ones. So in this case, this one over here also forms just hydrogen bondings. So the one that actually forms the most would be B, because it has it has dipole to dipole and hydrogen bondings. So D would be the answer for that one. And that makes sense, yeah. All right. Question 19. Which of the following statements about cyclohexane and benzene is correct? So we know cyclohexane looks like this. If I can draw it, it looks like... So it's this cyclic, like that. Okay, so it looks like this. And of course, benzene just looks like this, but it has these double bonds. And of course, these double bonds actually are resonant. So basically, they kind of move around. So basically, they'll look like... they kind of switch around. They kind of look like this, by the way. Because they're always moving around, basically, these double bonds, so they kind of look like this, basically. You can also draw them like this. Or, in actually some textbooks, they'll just draw it like this, because they are moving around, are resonant, they just draw a circle in the middle. So, also, because, yep, there it is. So, these are all benzene, basically, and this is cyclohexane. Both have structural isomers that are non-cyclic. Both have structural isomers that are non-cyclic. Now, I can understand that this one, hexane, can have some. I do think so. Like, you know, you could probably form, non-cyclic. I've never seen benzene having, benzene, especially this molecule, having isomers. I don't know. I'm going to put a question mark on that. That's actually confusing. We've never, especially in the textbooks, gone through this. So, never drawn isomers of these, so I'm not too sure. I'm going to put a question mark on that one. Both have the same average bond strength between the carbon atoms. Absolutely wrong. Now, why? Because you got to remember that this one over here only has, like, C to C bonds, like where it's a single bond. Whereas this one over here has C to C double bonds. And remember, C to C double bonds are much stronger in terms of bond strength. And you can actually see that on the data book if you're wondering. Also, let me just rub this out. This is quite ugly. Like this. So you can also see this going down here into your bond strengths. Here it is. So we can see that a C to C is 346 kilojoules per mole, whereas a C to C double bond is 600. It's around double, close to double the amount of energy. So they don't actually have the same. Absolutely not. Both are members of the same homologous series. Now, a homologous series means do they follow like the same formula, like a same, like for example, a homologous series is like alkanes, where they follow this formula. You can think of it like this. Do they follow the same? I don't think so. Absolutely not. This one has double bonds. These have single bonds. I don't think they follow any formula that follows those. Each carbon in a cyclohexane has one more valence electron than each carbon in the benzene. Rubbish. Remember that they will... How does... Yeah, no. So carbon always has 4 valence electrons. We know that. How's the valence electrons changed? They never change, they are constant. This has 4 valence electrons, the carbon here has 4 valence electrons, and the carbon here has also 4 valence electrons. They don't change the valence electrons. One doesn't even have higher, they all have the same. Each carbon cycle has 1 valence electron, then so that's rubbish, so A would be the answer there. I'm not too sure actually if it's A, to be honest. I think it's that. Yeah, I'm not too sure. I will probably check after, seeing if there is actual isomers of benzene and, non-cyclic ones. 20. So 20 says, consider the structural isomers of this that are aldehydes. All right, let's draw some aldehydes. Yep. You can draw some aldehydes. Wait, which of the following statements is correct? Yeah, and then there's 3 isomers. There's 1 isomer with an ethyl side branch. 2. So we actually need to draw them, actually. So we can look at the easiest one, which is C to C, which is linear. And we have the this aldehyde over here. We can also have... So basically, so that actually, so this like that, H, and we can have a CH here, a methyl part on the first, so that's on the second carbon. So you know how that's the first carbon, the second carbon. And then we can also have on the second one actually too. And I'll have on the second one, like that. And we can actually have a C to C double bond H, and we can have C's all around, so like C, 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 like that. Also, that's another one. Yeah, these are the only ones actually possible. All right. So there are actually 4 isomers, not 3. There is one isomer with an ethyl side branch. So this one has nothing. Oops, no ethyl parts here. This one is a methyl, not an ethyl. Methyl again, and these are all methyls here. None of them have ethyl. There are 2 isomers that have one methyl side branch. Yeah, this one has a methyl and this one has a methyl. The only 2 of them actually have one methyl side branch. One methyl, yep. Looks like C is correct. What about D? Each isomer has a functional group on the second carbon atom. The functional group, for which is the aldehyde, it only occurs at the first carbon for all of them. So yeah, not on the second, so that's also wrong. So choose 20C. Let's have a look at the next question. Let me just move this here. Okay, let's move it there. Okay, question 21. Which of the following represents a skeletal structure for 3-chloro-butyl butanoate? Okay, so I know this is the ester, of course, yeah? But 3-chloro? Now, normally we don't actually ever, like all the esters that you do in like year 12 are, as I've done so many past papers, I've never seen an actual, they've put something in front of the, like normal esters are so basic, they'll just write butyl butanoate or something like that. But then I've never seen this 3-chloro, like, of course in uni I've seen that, but I've never seen it in textbooks. So how would students know how to draw this, to be honest? I'll explain how it works. So just first draw butyl butanoate as the way you would draw it in terms of normal ester. So of course you have the, this is the part that's the carboxylic part here. So there's going to be 4 of them, butyl. Of course, don't forget that double bond, O. And of course, we have butyl means the alcohol part is also 4. So 1, 2, 3, 4. Looks like that. That's what it'll look like. Now, I'll explain how it works. So butyl is the alcohol part, isn't that right? Now, it's bonded with 3-chlorobutyl. I mean, okay, you know how this is the part that's the alcohol part? Imagine, okay, you remember how you'll count from 1, you'll count from, 1, 2, this is 3, 4. These are the 4th carbons. You're counting from 0 because you know how that's the OH when it was before it formed. This was the first carbon, by the way. This was the first carbon. So 3 means 1, 2, 3. There's a chlorine here basically. If I rub this out, that's what it'll look like, which looks like what? So that's what I mean. Like normally they've never no textbook. I've never seen a textbook question draw like esters are, in terms of that would have confused a lot of students, to be honest. Let's have a look. Not A, because A, can you see how this is where the double bond is? They're putting it on the left hand side on the double bond, the chlorine, which is actually supposed to be on the side of the oxygen. Same with this one too. You can see that the chlorine is actually on this side. It's supposed to be on this side. This one over here, so let's count how much there are. So 1, 2, 3, 4, 5. It's only supposed to be 1, 2, 3, 4. So that's also wrong. Yep. And the next one is, let's try this one. 1, 2, 3, 4. Yep, 1, 2, 3, 4. Perfect. And then 1, 2, 3. So 1, 2, 3. At the third one, yep, there's a chlorine and there's a methyl. Yeah, that's the one. I'm not gonna lie. I think a lot of students would have struggled with this one. This one's actually, because they've probably never done practice with. No textbook has gone through this part here. So, damn. Question. What is it? Question 21. Yeah. Next question. Let's have a try at this question over here. A triglyceride is reacted with methanol in the presence of concentrated, potassium hydroxide. The products of this reaction are glycerol and compound J. This is easy. This is just remember, this is called transesterification reaction, and this is how we form biodiesel. So think of the molecular formula of compound J, which is basically the biodiesel. It's the three fatty acid methyl esters. What is the molecular formula for this triglyceride? Really? Wait, this is like the sample question. I'm not gonna lie. This is like the sample question that was given this year. So we know, think of it, a triglyceride, we know it reacts with 3 methanols with potassium hydroxide as a catalyst, and it gives you, of course, what? A glycerol and 3 fatty acids. So what is the glycerol? 1 glycerol. So glycerol, you can actually find it in your data book. I don't know like the molecular formula for it, to be honest. So we can find it, just go down here. There it is. So this is glycerol. So there is 3 carbons, so C3. How many hydrogens? 3, 6, 8. And 3 oxygens. Perfect. So that's, yep, it forms one glycerol and then three fatty acids. So compound J, yeah, which is C19, H30, oxygen 2. So let me write that nice. Oxygen 2. Okay. So, of course, this is what we call, this is like balance. So it's really easy to find the amount of triglyceride. So how many carbons are on the right-hand side overall total? There's 3 here, and there's 19 times 3. So what's 19 times 3? But don't forget that plus 3. There's overall 60 carbons here. There's overall 60 carbons on the right-hand side. Of course, this one here takes how many carbons? So this one has already taken 3. So there has to be, C57. There has to be 57 carbons because 57 plus this 3 will make them equal. It's done. What about the hydrogens too? So in terms of hydrogens, so there's 30 times 3, which is 90. And here there's 8, so 98 basically. We have 98 hydrogens on the right-hand side. Here we have 4 times, so there we have 12. That's already taken. So what's 98 minus 12? You have 86. You have to have 86 hydrogens here. So 86 plus 12, and we will have hydrogens equal on both sides. Oxygens. What about the oxygen? So for the oxygen part, we have 6 here, and actually plus 9 because this has 3. This one already takes 3, so then this has to have 6. So this is your molecular formula for your triglyceride, which looks like D is your answer for that one. Not too bad. Question 23. When a triglyceride is reacted with methanol to produce glycerol compound J, H2O should be added to the potassium hydroxide directly because KOH is considered corrosive and causes skin burns. I have no idea, actually. Put the question mark on that one. H2O should not be added to the reaction mixture because it interferes with the desired reaction. And that's actually true. If you kind of think about it, we know that, think about it. If when the triglyceride, is getting reacted with this, remember, what happens if you react the triglyceride with water? Isn't it when triglyceride breaks down? Remember this reaction? When a triglyceride, it's a hydrolysis, by the way. It's a hydrolysis triglyceride. When it reacts with 3 waters, it forms 3 fatty acids, and a glycerol atom. So if you think about it, if we want this reaction, and if we have water, if water gets added, it's going to interfere because this reaction can occur, and that's not what we want. So B actually looks quite right in this one. So I'm going to put a tick on that. That actually makes sense. H2O should be added to separate the triglyceride from glycerol, since triglyceride is soluble in water. No, it's not. Triglyceride is not soluble in water. It's a fat. So it's like oil, basically. And it's very non-polar, so it's rubbish. D. H2O should not be added to the reaction mixture because it increases the frequency of successive collision. Absolutely rubbish. H2O, you dilute the solution, so you dilute it. You decrease the concentrations. If you decrease the concentration, there isn't a lot of collisions. Hence, it decreases the actual frequency of collisions. So B actually would be the best one here. B. Why is A? Then it can also explain why A should be wrong, because if water is added again, this reaction can occur and this can again impact. Yeah. So B is the best in that one. 23B. Okay. 24. It says Evelyn titrates 10 milliliters of 0.1 potassium permanganate with 0.1 oxalic acid. The half equation for the addition of oxalic acid in acidic conditions given. The volume of this should be added to reach the equivalence point is what? This is actually not too bad. So we want to try to find what? The volume of this. And we're actually given the concentration. So we just need to find the mole. Now, we know this already. So we know the potassium permanganate. We can actually find the mole of it. The mole of potassium, which is KMNO4. Permanganate is, well, think about it. So we know we have, so concentration is equal to NV. So isn't it just C times V? So it's 10 times 10 to the negative 3, because we're trying to convert this in liters, times 0.1, the concentration, and we get 10 times 10 to the negative 3 times 0.1. We actually get 0.001 mole of that. So because how is this actually very useful? Like, there's nothing we can kind of relate this equation with this equation, but we actually can. How? If you look at your electrochemical series, this is actually new in the study design, but if you can look at potassium permanganate. So if you go up here, it's actually in the data book now. So if you look here, it's right over here. This is the reaction. So let's write that down. So it's MnO4 plus 8 H pluses plus 5 electrons gives us Mn2 plus 4H2Os. Done. So what we can do, actually, think about it. What we can do is, so this here, by the way, this mole is the same as this mole because it's the permanent ions. So can we find the mole of the electrons for this equation? And we can relate that mole of electrons to this. So the mole of electrons for this one, so what is it? It's 0.001, the mole of this. What's the ratio? It's a 5-to-1 ratio, so you just multiply by 5 basically. And we actually get the mole of electrons. So we get the mole of electrons. Now this mole of electrons, remember, we know the mole of electrons. So now we can find the mole of the oxalic acid. So the mole of oxalic acid is basically 0.005 times, basically it's a 1-to-2 ratio, so half. So times that by half, and we get 0.0025 mole. So now we got that. Now, of course, it's now easier because now we just need to do this. We know that we know the mole of oxalic acid, and we also have the concentration. We can easily find the volume because remember C equals NV. So volume is just N over C. So what's the mole? 0.0025 over 0.1, which gives you, so that 0.1, we get basically 0.025 liters, which is basically the same as 25 milliliters. So 24D for that one. All right, that's actually, okay, that took time. 25, let's have a try this. A chemist, so for the questions is for 25, 26, a chemist runs a mixture of hexane, hexane 1-ol, and hexane 2-on through a high-performance liquid chromatography, HPLC column using a polar mobile phase and non-polar stationary phase. Which of the following shows the chemicals in order of the retention times from lowest to highest? This is actually not a hard question. This is nice. So if you think about it, think of it as like a paper. Like I was trying to break it down questions. Like think of it as just, okay, so imagine, okay, you have this here, and that's the HPLC. So remember, the stationary phase is non-polar, and we're talking about retention time, and we want lowest to highest. Lowest means like if you have a very low retention time, it comes out quickly. It comes out quickly, meaning that it's not highly bonded to the stationary phase, which is non-polar. So basically, the one that's the lowest is very polar. Basically, you're going from polar. And the highest retention time means that it's more strongly bonded to the non-polar because it's slowly down, like it's not pouring out quickly. It's taking its time. So yeah, you're going from polar to non-polar basically in terms of this. So think about it. Which one's, yeah, like of course the polar one is hexane 1-ol because it has strong hydrogen bonding. So hexane 1-ol. Then hexane 2-on is what we call is dipole to dipole, and then hexane is all dispersion forces. So this one here is basically non-polar. This one's very non-polar, so it should be on the right. It's not these ones. These ones have hexane, and then so it's D. Remember, hexane 1-ol is the strongest one in terms of polarity. So that's the one, D. Whereas hexane 2-on only has dipole to dipole, which are actually a little bit weaker compared to the hydrogen bondings. All right. Next question is 26. A chemist wants to determine the concentration of hexane in a mixture. Which of the following will provide information to allow the hexane concentration to be accurately calculated? Yes, so normally if you're using HPLC, we know this. When we use a HPLC, we normally use this graph. If you don't realize this, so in a HPLC, this is what we actually use to kind of, so you would have seen, it's like a calibration curve where this here is the concentration and here is the area. And so what we do is we'll calibrate this by having known concentrations of hexane. And then what we do is we, of course, go through HPLC and we can find that area. And what we can do is we can find the value of concentration by using the calibrated curve here. That's what we normally do. That's how we can find the concentration. Let's have a look at the questions. So A, writing a series of known concentration of hexane for HPLC column under the same condition. Absolutely, this one's the best one. Here it is, straight away. That's what we just said. if you, running a series of known concentrations of hexane through HPLC column under the same conditions. It's important to have the same conditions because some HPLCs, if you have different conditions, of course, it affects, if temperature is not the same, all these kind of stuff affects it. So this one actually A sounds the best. B, running the HPLC experiment using a non-polar mobile phase and polar stationary phase. What the hell does that got to do with, that has nothing got to do with like determining the concentration. Using the published retention times and peak sizes of standard hexane chromatographer. See, that sounds kind of correct, but the problem is, again, A is more better because you're using the same HPLC thing, and what you're doing is, it's much more better because, again, the thing that can affect it is having the same conditions. This one, A is more correct because you are using the same conditions. These ones over here are, just published retention times, which can have different conditions to your one. So, absolutely, that's... in comparison to the other one, A sounds better. Reducing this HPLC column temperature to achieve better separation of the compounds has nothing got to do with concentration, by the way. Determined concentration. So A is the best one. Nice. 27. Which of the following statements is correct? The presence of chiral carbon in a compound shown is clearly... The presence of a chiral carbon in a compound is shown more clearly by performing volumetric analysis than by eye spectrum. Rubbish! How's volumetric analysis going to give you... determined chiral carbons? Remember, volumetric analysis are used to determine the concentrations and that kind of stuff. So nothing got to do with the chiral carbon, because the chiral carbon, to find that, you need the structural. This is totally right. Then by its IR spectrum, again, IR spectrum is also useless, to be honest. It just determines the functional groups. It doesn't even tell you anything about how the structure, where the carbons are bonded and stuff. So not really good. B, the presence of chlorine in a compound is shown more clearly in its 13 carbon NMR spectrum than it is mass spectrum. Well, let's have actually look at this. 13 carbon NMR. The presence of a chlorine. So if I go to 13 carbon NMR, I think, you can absolutely show it there. There is some, you can see it there, actually. If I go down. Go here. Where is it? Okay, carbon NMR. So, you kind of can, in this case, you can see if you have, X is, of course, the, it could be iodine or, chlorine, any of those. So, you can see it if it's in around this range. But the problem is you can't really determine the presence of chlorine. But you could determine the presence of, bromine, all the, what do we call them? I fully forgot the name. But those bromine, those iodine, those chlorine, all of those values there. So, that's actually wrong. The presence of chlorine in the compound is more clearly... No, it's not really clearly. Then it's mass spectrum. The mass spectrum is can be a little bit more clear, actually, because if you think about a mass spectrum, you know how it's broken down into fragments, mass spectrum, and you can determine the molar mass of those fragments? If you can determine the molar mass and kind of relate them to, let's say the molar mass of chlorine is 35, I think, 0.5. And so if you can see some of those fragments, when they get broken down, you can see one that has that 35.5, it can actually tell you that there's a presence of chlorine. So B is actually wrong. Actually, I would suggest, from my opinion, I would suggest, the mass spectrum is actually better. You can actually determine so that's wrong, because it says the presence of chlorine in the compound is more clearly in the 13 carbon NMR than its mass spectrum. I think the mass spectrum would be better. C, the number of carbon-to-carbon double bonds in a compound is shown more clearly in a HPLC spectrum than by using iodine test on a compound. Rubbish. An iodine test is absolutely 10 times better in determining the carbon-to-double bonds. What the hell does HPLC got to do that? HPLC, you can determine the concentration, you can determine how polar a compound is. Nothing got to do with determining the carbon-to-carbon double bonds. D, the presence of a primary hydroxyl group in a compound is shown more clearly in a HNMR spectrum than by adding acidophilate potassium permanganate to a compound. Now, this is actually true because we're talking about primary hydroxyl groups. So the thing about acidophilate potassium permanganate is it really doesn't tell you a lot. It can tell you, there's a presence of primary and secondary because it works for both of them. But how do you tell the difference between the primary and secondary? That's why it's actually useless. Whereas actually HNMR, you can actually determine if it's primary. If it's, so D actually sounds better. He's actually correct in that one. Because, you can, so the presence of a primary hydroxyl group in a compound is shown more clearly in a HNMR spectrum, then, absolutely. Adding potassium permanganate is really it really doesn't, it gives you for both the primary and secondary. It works for both of them. So you can't really tell the difference between the primary and secondary groups. You can actually tell it by HNMR. So 27D, I would say. Question 28. Capsicum. This is a plant used to reduce inflammation and pain. One active ingredient of this plant is shown. Which functional groups are present in this active ingredient? So straight away, when they're talking about functional groups, so we can already see that there is this here is a hydroxyl group. So a hydroxyl group. This part here is actually an ether, by the way, an ether. This here is a phenyl group. So when it's a benzene ring, this is also a phenyl group, we call it, a phenyl group. This here is a amide bond, And there's a, carbon double bond. I think, yeah, they consider also carbon double bonds also like a functional group. I remember looking at it on the data book once. It was there. Where is it? I have no idea. I'm so confused where the hell is data book. How am I going to... So I think it's at the bottom actually. Yeah, here it is. Okay. Yeah, actual alkenes. Yeah, also those are considered. So alkenes are considered as also, are they called alkenyl? Alkenyl. All right. There. Did I aim everything right? There it is. Okay. So... let's look at this. Which of the following are present in the active ingredient? So the first one's alkaline, yep. Amide, yep. Hydroxyl, yep. This one actually contains all of them, so it's that one. What about the other ones? Yep, it's not an amino acid. That's actually wrong, so that's why. This one, carboxylic. Nope, there is no carboxylic acid there. It's like a C-double-O bond, by the way. So it's only A. Beautiful. Question 29. A reaction between sulfur atoms in proteins contributes to quaternary structure. Okay, if you don't know, the only compound that actually forms these sulfur atoms, like the reaction between sulfur atoms, is cysteine. An amino acid called cysteine. I remember cysteine. Where is it? Going down here. Show you where it is. Cysteine actually has sulfur in it. You can see. Now, there's two compounds that have sulfur. But this one actually, between it, actually does form. It's the only one that forms between itself, like cysteine. It forms these disulfide bonds where these are going to be these disulfide bonds. It'll be like a SS. And these are actually called disulfide linkages or bonds. And they're also called, in other words, covalent bonds, by the way. They're also covalent bonds. So yeah, you can call them covalent bonds or disulfide linkages. Disulfide is much more nicer. Let's have it. And let's have a look at the first one. Contributes to the quaternary structure through ionic bonding. Absolutely rubbish. So these, okay, remember, primary structure is only the bonds that are in it are peptide linkages or basically the covalent bonds. Peptide or /covalent. Secondary is the hydrogen bonding. Tertiary is all basically like ionic, dispersion, these ones over here, the disulfide thing. And quaternary is the same as the tertiary where it's all also. So it says contributes to the quaternary structure through ionic bonding. Now, it does contribute to the quaternary structure, but not through ionic bonding. These are covalent bonds. It doesn't have ionic bonding there. Contributes to the secondary structure through hydrogen bonding. Rubbish. Remember, it only forms, these disulfide linkages only contribute to the tertiary and quaternary. Leads to the formation of covalent bonds. Yep, they're also covalent bonds. And contributes to the tertiary structure. Absolutely, remember? So that actually looks correct. Another one leads to the formation of disulfide linkages, which is correct. They are also called disulfide linkages, and contributes to the primary. Nope. Remember, only tertiary and quaternary. So, yeah, 29C. Let's have a look at the next question. Salim is running a scientific poster to report on his laboratory analysis of a compound. Consider the following three statements. A 50 milliliter solution of 0.1 mole of HCl was placed in a conical flask. The average concentration is within the range claimed by the manufacturer. The table below shows the titers from the titration. Which section of this poster should include these statements? Okay, so let's look at the first one, I. A 50 milliliter solution of 0.1 HCl was placed. This is the method, of course. They're giving you like instructions. This is where you would put it in the method. So which one has that? It's not C or A then. So sorry, C and D. Then the next one is the average concentration is within the range claimed by the manufacturer. And the next one is the table below shows the titers from the titration. This one, of course, is the results because you are showing. If you're showing results, these are where you... if you're showing the values, these are where the results are. So 3, I know, is results. So it's actually C. And it makes sense. So the middle one has to be discussion, which, yeah, it is. You're just discussing the average concentration is within the range claimed by the manufacturer. This is where you would put it in discussion. And so 30C, perfect. And that's it. These are the multiple choice. I hope you can check your answers with these. Sorry, I didn't go really much in detail. I hope you smash your other exams, guys, and good luck with other exams, and good luck with life. Bye bye.